Okay, so this is your second slideshow about electrostatics, and now we're going to be talking about how we can visualize electric fields in three different ways. First one is force vectors, then field lines, and then equipotential lines. So let's take a look at each of those. Um, so force vectors, it's a force, it's a vector, has a direction and a magnitude. We're going to be showing the force on a positive test charge because that's pretty typical. We usually just look at the force on a positive charge. Of course, if you have a specific problem about a negative charge, you show the force that negative charge would be, which would be the opposite direction as a positive test charge in the same field. But especially if there's no charge there, we assume we're talking about positive test charges, so we can talk about which direction the force would be on a charge. Then there are field lines. Let me show you some force vectors first, and then we'll go on to field lines. Okay, this is a simulation at www.falstad.com/vector3de in case you want to know. Okay, so here's a charge, and all these little dots are positive test charges showing you which way a charge would go and how much force is on it. You can see there's more force when it gets closer because it's going faster. And another way to look at this is to display the actual vectors, force vectors. And you can see the direction of the force. This is showing the strength of the force by the brightness. So actually these dimmer ones are less force. Usually we show that with a shorter vector and then a longer vector here, but I guess that's kind of hard to do because the long ones would just go right past the middle. So those are force vectors. And this is a 3D simulation, so I can, see it from any angle. You can see the force vectors all go towards the object. By the way, since these are showing the direction of a positive test charge, what charge is this object? Pause the video and answer that question. Okay, hopefully you noticed that must be a negative charge. Okay, so those were force vectors. They're arrows showing the force on a positive charge in that field. The second way we can show the electric field is with field lines, and this is a new thing. These are continuous lines, kind of connecting all the force vectors and showing the direction of the field. And these lines don't always have arrows on them. Sometimes they do, so you can tell which direction they're going, but they show the direction a positive charge would move. Let me give you an example of that. Okay, we were looking at force vectors, but let's change that to field lines, and you'll see it'll kind of connect all the arrows into lines, and it looks like this. And the density of those lines, you could make it more or less. That's not what matters. What matters is the direction they're going. They're going into the object the same direction that the vectors were going, but they just don't show the arrows. We can also look at two charges. I'm going to make them one positive, one negative, and you can see with force vectors, a positive test charge would always go this way, from the positive on the left to the negative on the right. And a test charge over here would be repelled from the positive, right? And over here would be attracted to the negative. So in every place, every location, you could map which direction a positive charge would go. And with force vectors, it looks like this, but with field lines, it looks like this. So connects them. This is in 3D. You guys are going to be doing this in a lab in 2D. I could not find a non-flash simulator in 3D, unfortunately. But in 2D, it just basically looks like that. Something like you're going to be looking at pictures that look kind of like that. So I showed you force vectors, I showed you field lines, and now I'm going to show you equipotential lines. I think I guess diagrams, but equipotential lines is what I want to show. And And each line, everywhere on that line, has the same voltage. Let me show you what I mean. Okay, so you could think about how if you move a positive test charge away from this negative charge, you pull it away, it's going to give it more and more potential energy or voltage. And when you let go, it's going to snap back, kind of like a mass lifted above the earth. And that's not exactly true because this is so small. And if you get farther away, you get a weaker field. But imagine this is really big, like the earth, and you're just moving it slightly up off the surface. Then the field strength is about the same everywhere, so you're getting a higher voltage the further you go. But anyways, regardless, at a given distance or a given radius, the voltage on that everywhere on that circle is going to be the same. So if I display the equipotentials, meaning each of these lines along that line, it's equal potential or equal voltage. Each of these is a different level of voltage. Everywhere on the line is the same voltage though. So you could think of something starting up here at a, well actually, sorry. Okay, so this is a negative charge. So positive test charges are going to go towards it. So positive test charges always go from high voltage to low voltage. So the outer equipotential lines are the higher voltage going down, down, down to the lower voltage. And this is negative. Actually, it's a negative voltage. So it could be 0 out here, going down, down, down to more and more and more and more and negative. So these are equipotential lines. Okay, so you're going to be looking at these 3 different ways to visualize electric fields around charges. Positive charges, or one positive charge, one negative charge, a positive and a negative, or a positive and a positive, things like that, a whole line of positives. Force vectors are just arrows. We saw that. Field lines are lines showing the direction that a positive charge would move, and you can put an arrow on it, which would show the force vector as well. And a couple of rules about those field lines, they always start on positive charges and end on negative because that's the way a positive test charge would go. Their density kind of represents the strength of the force. You can see like the field lines are further apart from each other here and closer together here, so this is more dense, and so that's a stronger force. It's going to feel a stronger force closer to this charge. Actually, this is a positive charge, so it's going to feel a stronger force away from it than it does out here. It'll still feel a force away, but it'll be weaker. So the density shows the strength. And the other interesting thing is that the force vectors always go in the same direction as the field lines. So if you just connect a bunch of force vectors, you'll see the direction of the field line. And the other thing is that if you have a more charge, stronger charge, you generally you show that by putting more field lines into or out of that charge to show that it's a stronger force. That said, there's no rule. It's not like if you have 2 coulombs, you have to have 10 lines or something like that. There's nothing like that. This is all really qualitative. It's just a way to represent what's going on. And it was actually Mr. Coulomb who came up with this idea of drawing the lines of force to show how things would move in this field. Okay, and again, the last representation is these equipotential lines. So places where everywhere on that line is the same potential or voltage. And this is really basically kind of drawing a topographical map. If you've ever looked at a topographical map, say like a map of Albany Hill, it would be circles, right? Because at each one of these lines, it's the same altitude or the same height, right? If this is Albany Hill here, and you put a ball up on the top, it'll roll down the hill, right? So you could represent it this way too. You could show the positive charge up here at the top, and then these equipotential lines are all the same height, showing different heights as you move down that hill, and then you could go to negative heights for the negative charge down here. And equipotential lines would be the lines where everywhere around it is the same height. So you're going to be drawing those in the lab as well. Here are some examples of topographical maps. If you've ever looked at this type of map, which if you go hiking in the wilderness or something, you're in a place where you need to know how steep it is, right? If you're going to be going up this trail, and if you see that the topographical lines are very close together, probably that's a really steep trail. And if they're farther apart, that's a less steep trail because you got more distance to go that same amount of altitude. And this is showing how the altitude of each line, right? So that's the idea of a topographical map. This is representing a hill where this is the top of the hill, or yeah, it looks like this is a hill because they're getting bigger, but if they were getting smaller, this could be a valley or a lake or something. Okay, and then here's another example of going uphill where every line is a higher altitude, but everywhere on that line is the same height. In other words, if you dug a trench along the topographical line and filled it with water, it would stay there, or it wouldn't flow. And actually, farmers use that idea if they have a hilly field, the smart thing to do if you're farming it is to put your rows of whatever you're growing on the contours or on the equipotential lines, so that when you water them, the water doesn't just run off down the hill and take your soil with it. It actually stays there, doesn't flow anywhere, and just gradually seeps into the soil. If you ever go up, drive up north through some vineyards where they're growing grapes for wine, you'll see a lot of times people do the opposite. They'll run their rows of grapes down the hill like this, and you can just imagine that water when it rains just running right down the hill, which is not a good idea. Okay, so you're going to be doing this lab using an open source version of a PhET simulator, and let me show you that. Okay, here's this simulator, and it's based on the PhET simulation because the PhET simulation requires Java, and not everybody has that or has Flash anymore, so it's kind of outdated. But this one should work on any platform. You can put a charge in the middle. Here's a negative charge, so you see that the force vectors are going towards it. Again, these are showing strength by how bright they are, how dark red they are. So this is less strength, more strength. And then those are the force vectors. You can draw those yourself when you do the lab. And then it does not show the field lines, so you have to think about how these vectors would connect to make field lines, and you're going to draw the field lines yourself, connecting some of these vectors. But it does show voltage, and if I look around here, if I go around here, kind of keeping the voltage the same, negative 3.5, okay, right here, right? Oh. Okay, if I can keep it the same, I'm going to go in a circle around this thing. And that's because that's an equipotential line, or the same voltage everywhere, right? So this circle right here is an equipotential line, and if I move in and go to 5 volts, I can find another circle, another circle here. That's all 5 volts. And so you can actually plot that. Look, there's that equipotential line. You can move out, plot this one, right? So you can plot equipotential lines at different locations, and then you can draw those on your paper as well. And you've got negative charges. If you put more than one, you get a stronger field. And you have positive charges. You can put a positive charge. Okay, that just changes the whole picture. Or you can put another one. So you can kind of play with, what would the forces do? What would the field lines do? What would the potential lines? Okay, interesting. Interesting there to see what the potential lines would do in a situation with multiple charges. If you want to make a row of charge, you can put a whole bunch of charges just one after the other. And what you'll see is that you start to get a really uniform field. That the whole field is, especially look just above the charges, the entire field is pointing straight down. So this is kind of like the example I gave when I was talking about the gravitational analogy of just a straight down field, kind of like Earth's gravitational field. Okay, do the lab.